Hello everybody and welcome to my presentation on modeling the durability and service life duration of timber structures. My name is Christian Brischke. I'm from the University of Göttingen in Germany, working at the Department of Wood Biology and Wood Products. And it's my pleasure to present here today on behalf of the CLICKdesign team a recent state-of-the-art and some recent developments on durability-based design. When we're talking about durability-based design and service life planning, then we have to realize that this is rather less developed compared to structural engineering. Structural engineering, you can find plenty of literature, a lot of research has been done, this is very well developed, but only very few standards and handbooks are related to durability engineering. One is the ISO 15686 standard series on service life planning. This is not particular on timber structures, it's all kind of materials which are considered in this standard, but it provides the general principles and the framework for service life planning. And then there's another thing to mention, which is the Timber Service Life Design Guide, the outcome of an Australian 10 years research project, the Timber Life project, where a first comprehensive attempt has been made for service life planning with timber structures. When we're talking about service life and service life prediction of timber structures, then we usually refer to decay. That can be fungal decay, but can be also damaged by other biotic and abiotic factors. But when we're talking about decay, which is a global phenomenon, then we also have a relationship between the exposure on the one side, that is basically the different climate-related parameters and moisture temperature conditions. And we have on the other side the resistance, the material intrinsic properties, the resistance of the material. This can be related to wood chemistry, some extractives for instance, but also on anatomical features which affect the moisture performance of wood. So these are the two things to consider. But before we start with service life planning and recent approaches to do that, I would like to show you a little bit the historical background. There's no need to go too far back in history because pioneering work on service life prediction has been done in the late 1960s and early 70s. And Theodor Schäffer, who's working in the US, he developed a climate index to predict the biological climate-induced decay hazard for certain locations, the so-called Schäffer Climate Index. That was in 1971. And he produced such a nice map for the United States in this case. Later on, these decay hazard maps have been produced for many other parts of the world. After Schäffer, there was for quite some time nothing, silence. Not before the 1990s, there was the already mentioned Timber Life project in Australia, and a couple of manuals which were the outcome, as well as a software that you can see here, the Timber Life software. It was a huge 10 years research program, and a lot of basics have been developed in this project. In Europe, research started significantly later. There was a smaller German national project, so-called 25 sites project, starting in the year 2000, based on a lot of field work. Then a little bit later in 2007, we had the Wood Exeter, the first European joint project, where basics for service life planning were developed. You can see here as an example, another map introducing or implementing the decay hazard for the European continent. This was followed then by a couple of other projects, a Swedish national one, Woodbuild, where the ideas of Wood Exeter were further developed. Another one within the 7th framework, a Perform Wood project. This is more related to the standardization aspect of service life planning, in particular the standard EN 460, which is again or still under discussion today, where the use conditions are related to performance. Then, in another round of the Wood Wisdom program, there was a project called DuraTB, which stands for Durable Timber Bridges. And again, here on the example of bridges, service life planning was further developed. And finally, we managed to bring all the different groups in Europe that are working on this topic together in one joint project, the CLICKdesign project. And yeah, this is where we are today. But we have these many different projects, and they were very different in their approaches. But there was one thing that they all had in common, and that was the criticism around it. Been asked many times, isn't all this much too complicated? All this complicated algorithm, the complex background that we use, because many people think we know how wood protection works, don't we? Yeah, there are plenty of examples, historical buildings, modern buildings, very good examples of wood protection by design. So where do we need all this mathematical background for? Well, and to answer this question, there are different options. One would be a very long, more or less philosophical explanation that I could provide. But we decided to come up with a little exercise, with a little comparative study. And therefore, we compared the experience of humans, of experts, of laymen, and so on, with the predictive power of prediction models. What we did was a comparative study with different groups of wood users that were, in first instance, craftsmen, cabinet makers, carpenters, roofers, but also wood scientists, students, and researchers. We also asked architects and civil engineers, so different planners, and we asked laymen, non-experts, people that just go into a shop in a do-it-yourself market, customers, and buy and use wood products. And we asked them to predict the service life of different examples, of so-called example cases. These cases, or 18 cases, had a known service life. And the service life here was defined as the time between exposure and the first occurrence of fungal decay. And these 18 cases contained different designs, different materials that were used, and they were exposed at different locations all over Europe. And we showed this to, in total, 327 participants, which were from 14 different countries. I have to say most of them were here from Slovenia, and followed by Germany and Norway. And we tried to cover these different, let's say, target groups equally. So we had craftsmen here with scientists, students, architects, and also more than 50 persons without any specific wood background. So I don't want to show you all the examples here, that would span too much time, but just to illustrate how it looked, here are two examples. Case number one, which was a very simple thing, a bench exposed at the university campus in Ljubljana. It was made from large hardwood, was untreated, very simple setting here. And that was example number one. But we also had very complex and, in this case, even a bit exotic examples. This is a cycling track in a velodrome, also here in Slovenia, in Novo Mesto. And it was made from meerbau, a tropical hardwood, rather durable, still untreated wood. But it was fully exposed to the weather with notched planks, which were installed without any gap and put on a substructure of preservative-treated Norway spruce. Well, and as you have seen here for these two examples, this was the kind of information that we provided to the different people, to the participants of our little survey. And these were also the information that we used to feed our models with. Yes, because that was running in parallel, service life modeling, where we used different models. And the different models need to cover the aspect that I mentioned at the beginning. On the one side, we have the exposure. On the other side, we have the resistance. And both need to be somehow quantified, and therefore we used models. And the whole thing followed a design principle, which you all know, because it's basically taken from the Euro codes. And it says that the design solution is okay if the exposure is less or equal to the resistance. And both the exposure and the resistance have been expressed as a dose. The exposure dose based on temperature and moisture content, and the resistance based on the different material properties. And to fulfill that, we used, in this case, a three-step approach, three different models. First of all, an exposure model where we used climate data and design information. And the output was moisture and temperature conditions within the material, the so-called material climate, which was again then the input for a decay model. Decay, in this case, we focused on fungal decay. Could also done that with different other organisms. But here, moisture and temperature were related to fungal decay. And the third model on the other side of the equation was a resistance model, where we accounted for inherent protective properties, so extractives, for example, but also the moisture dynamics, the moisture performance of the material. Very briefly, I will show you these different models. There's a couple of publications where you can read more details about it. You will also hear something more about it by my colleague Jonas Niklewski. But in principle, we considered three parameters, three climate parameters: rain, temperature, and relative humidity. And we tried to predict the moisture content and the temperature conditions within a piece of wood within such a reference detail here. These information we then put into the second model, a decay model, based on field test data. You can see here a field test setup that we exposed at different locations in Europe and took daily data for more than 8 years. And then we ended up with such a dose-response relationship, this typical S-shaped curve, where the dose on the x-axis refers to different limit states, different levels of fungal decay. In our case, it was limit state number 1, the onset of fungal decay. This was per definition. And this way we could calculate a daily dose for each day by moisture content and temperature and accumulate that over time. So it's a typical time series here. So this is on the left side of the equation, the exposure side. For the right side, the resistance side, we made a little trick. So we knew that the critical dose for a wood species like Norway spruce, which was our reference species, was 229 days on average. That means we need 229 days of perfect conditions for fungi until the rating 1, the limit state 1, the onset of decay, is reached. So this is a critical dose, and that can then be multiplied with two factors, one factor accounting for the inherent resistance and another for the wetting ability. And this is wood species specific or material specific, of course. So this is a resistance model, at least its principle. And that can be used now to predict service life. I will show you that with a couple of slides exemplarily. So this is the overall equation to express the characteristic exposure dose. And we start with a site-specific dose, an annual dose that we can take from a map like the following here. So we have, based on meteor norm weather data, calculated the dose for many places in Europe. And you can see here the different zones with some hot spots in northwest Spain, with some cold spots in the Nordic countries and in the mountain areas. All this here is related to a reference location, and that is the city of Uppsala in Sweden, where the dose is 1.0. So this is a start, and then secondly, we can add some factors. We can multiply it with some factors, and the first factor is considering the local climate and wind-driven rain. This is what you can see here. We also have a map for the wind-driven rain loads, so you can see the effect on the different coastal areas. You can see a high gradient in wind-driven rain on Iceland, but you can also see that the majority of the European continent, the wind-driven rain load is very similar. And then we can also account for different protective effects, and it depends on the combination of the driving rain load and protective effects, which factor you need to consider between 0.8 and 1.0. The next factor accounts for the roof overhang, and this is based on some experimental data that we took from Denmark. We measured the moisture content on such a cladding. And you can see that there is a clear linear relationship between the ratio of the roof overhang and the distance to it on the one side and the annual dose on the other side. And this way it's very easy to come up with a factor that you can use depending on your roof overhang. So this is a design detail for a cladding. We can also have more design details, for instance here on a decking. There are different details in this decking. The very best solution is a vertical element, which allows for drainage and no water accumulation, no water trapping. So here the factor is less than 1. We have a design detail, which is our reference, a simple horizontal element, a horizontal board without any water trapping. And then we have a couple of elements which are worse than that. So where we have contact areas that can trap water. A horizontal contact area or a vertical contact area. Here we have a factor of 1.8. Even worse, the worst in this case, is a contact area where end grain of wood is connected with side grain. So here the factor is already 2.5. Well, in this way we can calculate the characteristic exposure dose for any example. So I've taken here a very simple balcony construction, which is located in Hamburg in northern Germany. And we end up here for Hamburg with 43 days per year. This is the annual site-specific dose. But then we have to multiply it with the different factors and end up with 66 days per year. So that means 66 days of perfect conditions for fungal decay per year. So and now we can calculate the resistance dose. This is based on different laboratory and field tests. So for Norway spruce, as I mentioned before, it's 229 days. If we select another material like European larch, this resistance dose is much higher, 1,347 days. And if you calculate one through the other, and you divide one through the other, then you end up with a service life, which is very simple. So that means 3.5 years if you make this balcony out of Norway spruce, but a little bit more than 20 years if you construct it with European larch, hardwood of course. So this is the principle for the calculation, and this is what we have done with all the 18 different example cases. And here are the results. So in this table, we have a first half of the examples, the first 9 examples. You can see different components, bench, stackings, fascia boards, bridge elements, which were made from different materials, in this case all untreated material, and they were exposed at different places. And here you can see the dose values, first the exposure dose and then the resistance dose, both expressed in days. And if we now predict the service life, we come up with the following numbers. So the first half here, it was between 2 years and 12 and a half. And finally, we compare that with the real service life that we know. And that was not so far from the predicted service life, I would say. So quite a good fit. Very similar picture for the second half, which is shown in this table here. So we have some examples which are with a longer service life, but I want to highlight at least two on this slide. First is the cycling track that I've shown before, and here we had a perfect fit. The predicted service life was 21.6, the real service life was 22, so that was identical. But we also have a negative example here, and that was a playground structure, some stairs on a playground, which were made from CCB treated Norway spruce, and the predicted service life was only 7 years. But in fact, it lasted for 28 years before first signs of decay were found. So here's a picture of this playground situation. And obviously, it was the inefficient data that we had for this particular wood preservative in combination with the material Norway spruce. So this gave us the wrong information, and we had to admit that we need better data for these kind of materials. If we now summarize the data from this from the model to see what the predictive power was, we have this little correlation graph here, and you can see there are some examples in green where the model was conservative, so the predicted service life was less than the determined service life. And I highlighted here the playground stairs that I already mentioned. But we also had some non-conservative predictions in red, where the predicted service life was longer than the real service life. Okay, let's have a look on the expert predictions now. The predictive power of the expert is shown here together with the model. You can see in gray what I've shown before, the service life on the questioning, and in green on the model. So again, the fit was not too bad, but we had one example, one outlier, which leads to this very poor correlation coefficient. That was case number 17 with an extreme long service life. That was this one here, the outside trim of a hunting cabin. And this was made from Norway spruce, but exposed in the north of Norway on Svalbard, with extreme harsh climatic conditions. And this reached a service life of 85 years. And obviously, almost nobody expected that, because nobody is familiar with these extreme climatic conditions. Yes, and this leads us to the problem with this expert knowledge, because what we see here for the wood scientist is that the average estimated service life is very close to the real service life. The real service life is here shown in red circles, and you can see the black bars is the average value. But then we have these little crosses, and these are the single estimates by the wood scientists. And you can see that the variation, the scattering, is very, very high. Same picture here for the craftsmen and also the non-experts. Quite a good fit on average, but a huge variation of the results. So in other words, that means that you have to ask many people, 50, 100 people, take the average, and then you get a good estimate. But otherwise, the information is not very useful. So this leads us to a little conclusion. What was the outcome of this study? We've seen that the model gave very generally very good fit, but we have also learned that we are lacking data for some factors, for some materials, but also for some other parameters like the compass direction. When we look on the experts, now we see that also they, on average, gave a good fit, but suffered from drastic scattering. And by the way, there was no benefit of asking wood scientists or craftsmen. Yeah, also the non-experts could estimate how long a piece of wood will last under certain circumstances. And we have seen that the knowledge is quite often limited to the own experience. One example, we calculated the average predicted service life of all the 18 cases and sorted them according to countries. We have seen that the Norwegians um, predicted 14.3 years on average, while the Germans gave only 10.5 years, followed by the Slovenians with only 8.8 years. So there is a descending order which is following the climatic conditions. So in Norway, where the climate is rather harsh, people expect longer service lives from wood. In Slovenia, where the climate is rather humid and warm, the expectations are lower. Yeah, and in Germany, it's something in between. So this has to do with your personal experience and your subjective expectations, of course. Yes, so what is now the benefit of mathematical predictions model? They are free from these subjective expectations, of course, but we can implement experience data because we can use different sources to feed such a model. And such a model can be used by anyone, by experts and by laymen. That is a big advantage. Coming back to the initial question, isn't that much too complicated? I have to admit, yes, indeed it is. But with CLICKdesign, we try to make it as easy as possible for users of such instruments. So this is what we're working on, producing better models, more precise models, but also coming up with a very user-friendly software to make it as easy as possible for all kind of users. And this should help wood as a building material as such. So I hope that I could give you an overview about the current situation and also about the approaches that we are following within CLICKdesign. And with this, I would like to thank you for your attention. Thanks for listening to my presentation. Thanks a lot.